My name is Ólafur Waage. I am a senior software developer at TurtleSec AS, which is a consultancy company in Norway, Oslo, Norway. And you can yell at me on Twitter if you want. A lot of people do. They seem to like it. Yeah, I work with TurtleSec. We are a consultancy company in Oslo, Norway. We also do training at all sorts of conferences. Not this one though, but yeah, if there's a conference training, you will usually find us. Good stuff. I must go forward where I have never been, instead of backwards where I have. Like a good philosopher quote, right? But that's Winnie the Pooh. Yeah, good stuff. This is a classic slide, right? What this talk is and what this talk isn't. We're not going to be focusing on game development. You don't need to know much about game development. But the thing with WebAssembly is that it's really nice to use a game. It's a visual example. There's a bunch of code. There's interaction. So it's a good way to do that. And yeah, this talk kind of started with me making a game in WebAssembly and basically hitting my head on all sorts of things along the way. And I thought, like, this is interesting. So let's teach that. This is not going to be a very comprehensive WebAssembly talk. This is like a WebAssembly 101. There's a bunch of talks, I think from CppOnSea a few years ago, that go into all sorts of dark details about WebAssembly. And the basic idea is more about being pragmatic. There's going to be quite a bit of code examples, and I have a repo, and you can go and play with it after that. And all of the examples there have scripts to build it, so yeah, you can have fun there. So, what is WebAssembly? How can something be neither web nor assembly? WebAssembly, you can think of it as a binary format that was originally designed to allow for performant execution of code within browsers. That was kind of the base idea. Announced in 2015, working draft in 2018, W3C recommendation in 2019. That's kind of like getting the ISO thumbs up for us C++ folks. But the thing with WebAssembly is you can think of WebAssembly as the target output from any language. We will be using C++, and we will be using a thing called Emscripten, but there are, it's like with assembly, it's just, assembly, it's just a target generation. So think of it that way. The text version of WebAssembly kind of looks like this. So that's kind of the assembly part of it. You have a function definition, it's called getBoardSize. We're also exporting the symbol. We take there's an argument there. This is the return value. We have a value. So this is, a good way to think about it is it's a stack-based language. You put things on a stack, and when you pop the stack, you pop the last thing off the stack and you can return that. All right? And yeah, like I talked about in the beginning, a lot of you associate WebAssembly with games. And even though, yeah, we're going to talk about games, it has quite a bit more to offer. And here are some examples that you might not thought were written with or using a WebAssembly. Someone took the Windows calculator and just, yeah, this is the WebAssembly output of that. People talk about Figma. It's not all WebAssembly. There is some there to help with some things. So this is not pure WebAssembly. There's a bunch of utility things there. People made like a Photoshop clone. I think Adobe is porting a lot of stuff over, and I think they use WebAssembly for most of that. So yeah, you can think of Photoshop or photo editing. But it's not only user interaction type things. Tensorflow Js, which is machine learning, yeah, is running on a WebAssembly background. They got quite a bit of speed up. And this was a case study with, I think, protein folding or DNA analysis. And there was a 20x speed up in their setup. So one of the benefits of it is there might be speed up. It's not always this magical. Sorry to say, this is not a golden bullet, but it's lovely to see things like this. So we will be using a thing called Emscripten. This is WebAssembly before WebAssembly. Emscripten started with a thing called asm.js from Mozilla. This is a precursor to WebAssembly. The idea there is to more generate basically a subset of JavaScript. So you would write your low-level code, it will generate JavaScript, and then we would run JavaScript in the browser. That's why it's called asm.js. Yeah, it had its benefits, it has had its flaws, but Emscripten kind of came out from there. Yeah, this is where that came to play. It's based on LLVM and Clang. That's the tool chain it's using. So think of WebAssembly just as a target output from that. It gives you quite a bit of binary outputs, so the WASM files or the WebAssembly files, but it also generates for you JavaScript and HTML files. And we'll go into that. So for those who are playing at home as well, I see you didn't bring your laptops. That's fine. It's okay. Text editor we're gonna use is VS Code. I'm using WSL2 in Ubuntu 2004, and here's the repo. Don't mention that thing in the middle. So when you are setting up a development environment for WebAssembly, you say sudo your favorite package manager. You install Python and Cmake and Git. Then you git clone the WebAssembly repo, or the Emscripten repo, sorry. Go to that folder. Yeah. If you're updating and you have it, you have to do a git pull. You call emsdk install latest, which is a script they have in that folder, which will run some output. And then you can activate the latest, which means there's an internal state there that says we're going to be using this version because they have this feature where you can swap between different versions. And then they recommend sourcing an environment variable. This is mainly to get the compiler in your path. And you can also put this in your bash.rc or something similar. All right? So then you have emcc. You can get the version. You will get output something like this. Or you can say which emcc, and you can then see it's in some folder that I have. So this is the compiler we'll be using. And think of it as like a LLVM Clang-like thing. Cool. So that wasn't that bad. And now we have an Emscripten compiler installed in our system. And it's time for the hello world, right? We always need one of these. There are a couple of more steps though. This is a C hello world. I did just because I thought that was funny. So include studio, hello world, new line. Yeah, classic example. And you can run emcc hello world.c. I mean, that seems good. But what you get out is actually two files. You'll get aout.js and aout.wasm. And you can now go. Since I have the keyboard, I can be very, very flexible here. Go to my the terminal. Here. And it's the hello world. So I can just say build. And I'll get out the files, aout.js. How's the size for those in the back? Good, bad, more? Maybe we'll do this one. Everybody happy? I think so. Here we go. Cool. Okay. So now we have these. There's a thing called node, not noise, node, which is a JavaScript environment you can run things in. And if I can say a.out.js, I get hello world. That's pretty neat. The thing with build, it's just the emcc. So there's also an emcc hello world C, where you say that the target is hello world.html. It's not exe. So this is one of those weird things. You'll get a hello world HTML. You also get the JavaScript file and the WASM file. The JavaScript and the WASM file are the same thing as we got before. They're just named. And the HTML file is a different thing. These are quite big files. There are a few thousand lines each. So, yeah, we ran it in Node. That was just fine. So let's just open the HTML file, right? Let's just double click on it and it should be fine, right? Some of you know what's happening. No, that's not going to work. So wall number one, of course there's going to be a problem. So browsers don't like opening random stuff, which is, I mean, smart, I would say. There's a thing called cross-origin resource sharing, of course, which means that if there's a standalone HTML file that you have, it's usually fine. If you then want to open other files somewhere on your hard drive, it will not allow that. That's going to stop. So any file / or relative paths, like, no, that's not going to work. So we need something. So for a hello world in the browser, we need the web server, which is quite a bit of step up that we have to have. Nice thing though is that Emscripten has a thing called emrun, which is a very simplistic web server. If you want to go further, I recommend something else, but for like a very simple task, you can use emrun. So it's good enough for us for now. So if I then say emrun, give it the port, and hello world, I would get this lovely little output. But let's do that. Close this here, I think. So this is the repo. So you can run these yourself. So I can say actually build HTML. I'll get the HTML files, and then I can say run HTML, which will run the emrun, and then I have the browser. So down there is the debug output, or like the console output. So any printfs or these logs you have will appear there. And then the thing above is what's called the canvas, and you can draw on that. Cool. Happy? I would think so. Okay. So let's look at the game we'll be making. We're going to make a simple sliding puzzle game, similar to games like Threes and 2048. Yeah, that's the next thing. So in this project, let's close the server very violently. Let's go to 1. Yeah, that's the better one. I needed that open. I knew I needed that. Projects, WebAssembly, here. Yeah, this is a game. Very complex game. If I'm using the cursors up, down, left, right, so here I click left, I click up, down. It will merge boxes that are the same number. So if I do left now, it will merge the two. Again, merge. So you can have fun moving all these boxes and trying to merge them. So this is the game. The game itself doesn't matter much. What matters is that there's an interaction, there are graphics, there are... This will cause problems, which is the fun thing about it. If I go here into the game is basically an update function, a draw function, and then a main, which will set things up. And then we have a few event listeners. So this is kind of normal JavaScript things and some key events. The update functions are just calling updates. Or I think I have called box, doing some logic. Draw is calling the draw of the boxes. Main is doing some fetching the canvas where I can draw into and clearing the screen and calling update and calling draw and then restoring the screen back to. So, and the key down event is a regular. This is a callback to when I press keys. So I can set the event listeners, and the actual game logic itself is here. If you want to browse that later on, you can. It's not great code, but it's enough to get things moving, right? And then the index HTML is we include the box JavaScript file, we include the game, and then we have a canvas. That's it. And yes, this will cause issues. Cool. Oh, I can close this and this. Okay. So we have some JavaScript, we have some logic and some game. Let's convert that over to WebAssembly. There are two ways to do this. We can keep the drawing part, so the graphics part of it in JavaScript, and do the game logic in C++, or we can do everything in C++, and we will do both, and all the fun things along the way. So, I mean, converting stuff over. Let's start to take a function and just convert it to C++, right? And some of them don't even need to know about the game state, so they should be the first ones, right? So here's two fun ones. When you press one of the buttons, a new box appears. We just want that to appear randomly. And we also want to check, are you outside the box? We don't want you to move outside the box. So let's start with the outside of the box one. This is the whole thing. This is everything we would need. But there's a few things we need to talk about. Include Emscripten. yeah, so that's basically all of the utility functions we need for that. The Emscripten keep alive that's there, it's basically to prevent the compiler to optimize away the function, because there is no main. There will be main later, but in this case there is no main. But otherwise the function is identical. If you go here, yeah, it's the same function, not very complicated. We do extern C to prevent the name muggling, so we have a nice name on the JavaScript end. And then, okay, we can compile this. Compile line looks like this. We do G and G source map to get some debugging info. We say no entry and standalone wasm. So this is there's no main file and no main function. And the standalone wasm is basically saying I don't want the JavaScript file and I don't want the HTML file. I only want the wasm file because I'm going to do everything else myself. And then the logic and the file. Okay. So in my on my JavaScript end, I do this. So there's a WebAssembly instantiate streaming, and then fetch the wasm file. You don't need to know, it's just to read the file. And then when reading of the file is done, we call a function with the results. And within the results is the instance of the file. And within the instance of the file are all the exported functions that we have. And one of the exported functions is outbounds. So I can just turn that into a function, turn that into a variable, and then I can call that function. And this works fine. We're happy so far, okay? We're not going to run this direct example, but in this case, we are fine. Okay, so let's do the next one, because we're fine, right? All right, get random coordinate. It's a math.floor and a math random. No, that does not work. Because where we're going, there is no operating system. You are on your own. When you have a standalone wasm file, there is nothing. There's no operating system level functionality. This is what they talk about with the sandbox. That there is the wasm file. The wasm file will be loaded into the browser, and that's it. Anything else that it needs either needs to be in the wasm file or provided. So you are all on your own. So, I mean, that's a problem, right? How do we? I don't want to reinvent everything every time I'm writing this library. So using random, calling timer functionality and operating system level things has to come from somewhere, right? So thankfully there is a solution to this, and that is this .js file that we saw before. The .js file that we saw before is Emscripten providing to you the stuff that you needed. You did something in your code, you needed something external, we're going to provide that in the JavaScript file. Okay? So let's learn about that. Let's do that ourselves, because doing that ourselves will teach us a bit about how this works. So we wanted random, right? We want to call random. Emscripten has a thing called Emscripten_random, which is a function, which is from the header that is provided. This maps to math.random within JavaScript. Okay, this seems to be the thing that we want. Cool. Gives us a float, range from 0 to 1. Yeah, this seems to be the solution. Cool. So this is now my code base. Let's ignore the function that we had before. Let's just focus on this. So my get random coordinate function is then just going to call Emscripten random and get the value. Cool. All right. This is the HTML and the JavaScript that we're doing. It's the same as before. It's called function in this case, but it doesn't matter. And then I do the get random coordinate. I want to print it out. Okay. Who here thinks we're happy? Who thinks this is good? I see some smiles saying that no, we're not happy. Because we have an error. This does not work. And this error is quite weird for those who are seeing it for the first time. Type error, WebAssembly instantiate, import, module env. Module is not an object or function. There's nothing env here. There's no env that we're talking about. But what's happening here is this import object that I haven't been talking about, this second argument into the instantiate streaming that I kept empty at the beginning. This is the environment that we are then providing to the WebAssembly. This is the connection to the outside world that we're giving to the WebAssembly. Think of it as maybe the linker. Think of it as the operating system. It's the external world, right? And it's called env. That's how it's mapped. So that's an object. So, okay, I don't know anything more, so let's put env there, and we get another error, which is within env, function Emscripten runtime needs to be callable. And what this means that within env should be a function, the function called Emscripten runtime. So why is this happening? So this is the text output of the WebAssembly that we have so far. This is it's called the module. And you can see that from 00F5 and down, that's our function. Get random coordinate, it returns an I32, we're exporting it. And then in F9, if you can see that, there's a call to env.enscripten runtime. Okay, so we want to call that function. And the rest is some fun that doesn't matter right now, but we're calling the Emscripten runtime. So if you go to the top, the 21, the second line there, that we are basically promising to the WebAssembly that there is going to be something on the outside called env.emscripten runtime. So again, this is why I think of it as linking. Think of it as something external. So I can put the function. I call math.random within that function, and that works. We're actually happy. So the function, let me see, I have the time here. So the function within the C++ end is calling a JavaScript function and then coming back. So that's why I think of it, as a sys call. Like, this will take time, this might be slower, but we're not providing the functionality. By the way, you can just return whatever you want. You can return a 4, and that's going to be your random thing. Okay, so with this, we can actually port over the rest of the game logic. There's not many hurdles we're hitting there. The board is an array of boxes. That's not very interesting. And the gameplay is like, the game logic is there. There are not many other issues. But now, because in this instance, we want to do the game logic on the WebAssembly end, but we want to draw on the JavaScript end. So now these two need to communicate, okay? So, wall number 3, where's the data? I have this simulation, this state on the WebAssembly end. I want that now. I want to be able to call that on the JavaScript end. So, we can communicate between C++ or WebAssembly and the JavaScript side using primitive types. WebAssembly has certain guarantees about primitive types, like the endianness and the size of integers and floats and those things. So that's covered, that's settled. As soon as you have compound types or collections or that kind of thing, you will be running into trouble. Like, you could look at the memory for a std vector, but in JavaScript, there isn't a thing called a vector. They have the list and whatever they're doing. So those 2 bits of memory don't match. So you need to convert them or get the data out somehow. They have a thing called Embind. If you have complex classes you want to map over, so with Embind you can say, like, I have a class. It's called my class. It represents this type on the C++ end. The constructor looks like this. I have a function called this. I have a member called that. The class function is the static. So with this, you're basically saying, I have a class on this end, and this is how you communicate with it. So it will create something on the JavaScript end to convert back and forth. So now you could return that type. You'll be happy there. They also have utilities, like for vector. So you can register a vector. You say, like, I'm going to be using a vector. It looks like this. It has this type. You can register it, which means that you can then now use it as a type on the JavaScript end. Okay. You can even define a block of memory if you want. If you're that daring, so you can just say, like, here are a bunch of bytes. JavaScript is going to write to it. C++ is going to write to it. We're going to have a great time. So, yeah, you can even return a pointer to JavaScript, which is also very funny. But yeah, buyer beware. But have fun. So, I mean, kind of deliberately, I wrote the game logic in simple primitives, so we can actually convert everything over. So let's actually look at that implementation. So that was 1, 2 was the hello world, and 3 is game logic. So The building of it is the same. I added C++17 for more fun. Let's make it a little bit bigger. I can do that. But otherwise, it's the same arguments that we had before. Run HTML is the same. I'm sorry for the mount. It's just a way to get the Chrome to pop up. Our JavaScript looks like this. This is the same, the object. Ignore this. This is an experimental feature, but it will yell at me if I don't define it. But it's the same. I have the environment. Emscripten random, return random. I load the game logic, and here I am saying that within the instance, I have all these functions: the utility functions, the update, the get coordinates, get width, get information about. I have the key down event for the keyboard functionality. The drawing is the same as the other one. So that is the same, and the main is the same. So if I minimize this, I have the draw, and I have the main, and yeah, the rest is the same. So instead of having the update part, I am loading a WASM file and then fetching the stuff that was exported. And the C++ part of it is just a collection of the functions. I have the coordinates, I have outbounds, is empty, it's the game logic, just ported over. It's a little bit of code. I also have then the get board size. So here I have the functions to get the state out. So when I call this from the JavaScript end, they will give me the state. Forgive me for my sins, they are global variables, but yeah, that's gaming for you. And there's a box, which is the box that you have. Okay. And you can yell out questions while I'm doing this. That's totally fine if you have any. So I can build. Yep, I can ignore this error. That's fine. Run HTML. There. So here, it's the same game. The drawing is still in the JavaScript end, but this game state, what boxes are where, and even the transition, the moving over, the animation of the boxes. This is on the WebAssembly end. So again, there's no difference. Pressing all the fun buttons, pretty smooth. So this is the bit that's interesting for people that aren't into gaming. So here we have a C++ code base. We're exporting out the functionality and then calling it from the JavaScript end. So if you have a library, if you have a tool, if you want to keep the code base the same, like, we have this thing that we've written, that is this library or whatever we're doing, that we're using on a command line or whatever, we also want to be able to use it on the web. You can then compile it over and you can have the same code base. Just export the functions. So this is the bit that's interesting for people who aren't into the gaming bit is, yeah, you can export these functions out. In this case, as the game, doesn't matter much, but yeah, you can do that. Cool. Any questions so far? Thoughts, angry rants? No? Good. Yes. What's up, Jan? Yeah, so basically anything, anything that's not within the WASM file itself has to be external. So if you want to, for example, download a file and then get the data from the file into the state of the WASM, you are doing this round trip of, if I go here, because we defined these functions that we're exporting, go to the, I minimized it, right? No, it's the wrong one. Not number one, number two, then, why am I lost? Game logic. Here. With all these functions that are here, like this is the communication point. Like this is the, here for example, I want to get X coordinate. This is the function I'm exporting to the outside. So it will just return the value from here. Then in my JavaScript side, no, not this one. Here, I am exporting the functions from the C++ side. And I can use these functions. Here's is box empty. That is being called probably within the update or draw here. I'm just using it as a function. So if you would need something from the outside, which you can if you're running things in JavaScript, you can download the file and whatever. When the file download is done, you could then call a function that you have exported from the WASM side. When you call a function, you can give it the bytes. So then this is the communication point. This is the layer that is kind of the hard layer that you have to communicate between, either sending data from the WASM or giving it data from the outside. And again, like think of this as the syscalls. Like this will be expensive, like relatively expensive. But if you're not doing this very often, then that's okay, right? I mean, for example, I am calling in main. Where's the update here? I'm calling the update function. This update function is on the C++ end. You can see here, this is being called 60 times a second. And this is updating this game logic. So, I mean, there is a cost, but it's not like, it's not outrageous, right? Was it good? Good. All right. So we've gone this far. What's the time? Oh, wonderful. Wonderful. Okay. So now we basically have everything except the full C++ version, right? So let's move that one over as well. So we would like to draw basically the game graphics on the WebAssembly part as well. So how would that work? So Emscripten actually has support for that. Emscripten has built-in support for SDL, which is a graphics library. It also has all sorts of other utilities that games use a lot. It also has support for SDL2, but you need to download it first. And I'm actually going to use that just to show you that how that can be downloaded. The only thing you need to do is to put in the flags, use SDL2, and use SDL TTF, which I'm going to use. TTF is the font library they have. And since we're going to use SDL2, we're going to use the generated JavaScript code. So we've gone from we're going to write the JavaScript glue code ourselves to we're going to use the JavaScript file that Emscripten makes for us. And actually, I can actually show you later how that file works, and it's the same thing that we've been doing. So instead of creating the import object ourselves and filling it with that one function that we wrote, we're just going to let Emscripten do that for us. And it's going to write quite a few more functions for us. Now we actually have a main. Our main looks like this. The create box creates just an initial box to start with. The SDL init is just to set up the SDL library. Some of you who have been used SDL might wonder, like, what are you rendering to? It will default to a canvas in the HTML. So if there's a canvas that has an ID of canvas, it will use that. So I'm creating a 400 by 400 pixel canvas to write to. I will initialize the text library. I will open the font. And then, yeah, the bottom line is kind of the important one. Emscripten set main loop. So my the update and basically the main loop or the main function that was on the JavaScript side is now moved to C++ because everything is in C++ now. But we can't just run this in a loop. If I would just make a regular loop on the C++ end, the JavaScript, or basically the front end part of it, would never run. It won't work because the Emscripten, the WebAssembly, is using up all the resources because it's never ending, because it's running forever. So what we do instead is we will give up the context until Emscripten says you can run now. And when Emscripten says you can run now, we will run this function, which is called game loop. We will do our thing. We will update the game. We will update the graphics and the texture, and then we will back out until Emscripten says you can run again. And this is at the same tick rate as Chrome, which is, I think, 60 FPS. So every 60 times a second, this function will be called. Okay. Then I port over the rendering code. Because the game is pretty simple, I'm just drawing a box, just a red box. It was kind of deliberate to do that. I'm going to wait with displaying the text for now. So we had moved over the rendering code. We seem to be happy using all the tutorials and all this stuff. Everything compiles. We seem to be happy. And then I run it. I see the red box pop up on my screen. And then I get this. Runtime error. Cannot enlarge memory array size to some bytes. Yeah. So here's the next wall you will hit along the way, is that the sandbox isn't infinite. The sandbox has an initial memory size. And up to this point, I've been using the default, and it just happened to fit. But now, since I am allocating much more on the WebAssembly end, the graphics and all this stuff, loading these files, no, I need more memory. Yeah. So these are the three that you can use. You can set initial memory, total memory, and allow memory growth. So you can be in quite a bit of control of the memory. So when we do that, it compiles, and we see the box drawn on the canvas. Okay, I mean, it's kind of boring so far. We just had the red box, but we want the little text, the little number to appear as well, right? Yeah, which is, again, the next wall, file not found. As I talked about before, there is no file system. There is no, yeah. So how are we going to load files? How are we going to, yeah, there is no C drive in the sandbox. Yeah. So that font file, which is the TrueType font that I want to load, it doesn't exist. There is no file system. We have to provide the files in some way. What you can do, there's two ways. You can embed files, or you can preload them. This is more of a technical, like, what does what mean? What I usually do is preload, so they will be there with the WASM file. And what you do in the compile arguments is you say preload file, and you give it a folder. So you say any files within this folder are preloaded, and then you do the @ symbol, and then you do a path. The path after the @ symbol is the path that the WebAssembly will recognize. So if we go back to, there was this one, you can see how I'm loading the font is /assets and the font name. That is because I did this. So I say that the folder called assets, that's one below me, is /assets. So all the files are there. This actually works. Yeah, okay, I had the examples there. Oh my God. It's beautiful, right? It's almost like I thought I had. So, but this is not the only thing that Emscripten will give us. Emscripten also provides helper utilities for more modern development tools like Cmake. It's a macro or like a utility you need to run before. So you say em_make or em_cmake. What this actually just does is it sets up the environment for you before you call Cmake. So don't worry too much about that. But this means that we have full Cmake support. So what I've been pulling from is a Cmake file. That's why I've been showing you just the snippets. I really like the third line. The Cmake executable suffix is .html, which I always think is funny to look at. But otherwise, I have, yeah, I have O2, I have the G source map, using SDL, setting the memory. The shell file is telling it what HTML file I should have when I load it in. But notice the top one, fsanitize address and profiling. Because, like I talked about in the beginning, this is an LLVM and Clang environment. So the memory error we got before was a sanitizer warning, right? It wasn't something magical. So these sanitizers that exist can help you in this environment as well. So sanitize address, yeah, you can have those features. So we should have everything running now. Let's see that in action. And I'm actually going to show you one thing first, because of course I forgot a thing. Of course. So if I run this again, not caps lock. I did the thing wrong. There we go. So this is the thing. This is the version before, where I had the rendering within the JavaScript part. We can actually use the Chrome development tools. So if you print out to the console, it will appear here. If you go to performance, and if I hit this, and I move the boxes a few times, and I hit stop, I get a heat map. So I can actually optimize and look at the performance of the thing I'm running. I can now go here and see that, there is a request for animation frame. So here's the call to main. It took 0.64 milliseconds. The call to draw took 0.18. So all of the development tools that you have within Chrome are actually available here. There's another neat thing. If I zoom out, I don't have it set up. Yeah, okay. You can sometimes also see the actual frame of the game. We'll save the game frame here. Maybe share below. No, but anyway. Yeah, you can have the profiling tools. And you also have, go to sources, you have the C++ code. So what I can do is I can say, here's the update. I can put a breakpoint. I can see here's the stack, which is, I don't like that it's called like this. There's probably some way to fix that, but these are your stack variables. But yeah, I have a breakpoint here. I think it's F10. I can go in. Oh, not that F5. Fine. I'd like to continue. There you go. Yeah, so I could put breakpoints. I could look at the values. Yeah. So this is kind of instead of, basically like one of the questions that pops up is, what about debugging? What about like normal development flow? Is that, yeah, you can have this. And the reason, because I have an issue, the reason is why I showed you in this end is that it doesn't work on the other one. But I have not found out why. But, we will look at this. So if I then go to 4, so I can write the build. You can see the classic Cmake build process. And the linking of the game.html. Here we go. And if I go to build, it's the same file set we had before. We have the data, the HTML, the WASM files, and so the data file is the embedded stuff that we had. And the .js, so these are the same files, but in a more of a Cmake format. And then I also have a little Python server, because Python has like a simple HTTP server. I did one change to it that if someone requests a .wasm file, I reply that it's an application wasm, so it's a bit nicer to me. So if I say Python server.py, run this, and then instead of doing this, I think it is build game. It's the same. So we have the same game here. For those with keen eyes or very great vision, you might see that the font is slightly more jagged on this end. It's because I don't have anti-aliasing on. But each box and each font is a texture on its own, which is then drawn onto the screen. And in the same vein, I can go into here, go into performance, run this a little bit, hit stop, and I will get these function calls. So I get the C++ ones. So I can see that like the STL calls are taking this amount of time. There's these shader things that are happening for the text. I can see that the game loop is taking 2 milliseconds. The draw taking 2. Yeah, so this benchmarking here. And this works even if you're not making a game. If you're just calling these functions, you can get this thing out. The same thing for memory. You can do memory snapshotting. I can profile, do something. I can see the memory. And I think this one also has that if you do it twice and you do something, you can do the diff where you can see the size of the allocation. So these development tools here are very nice. Very good. All right. So, questions so far? Yes. So I kind of mentioned before with the Embind. Yeah. So it's talking about the serialization between the JavaScript and the C++. They guarantee things for the primitive types. So if I do like WebAssembly, because for everything else, it has to be done by someone. What is usually in the case with Emscripten is that it will do that for you for some of these cases, so you will get a lot of the functionality before. But the reason why I showed you with the very simplistic case is that someone did that for you. Someone implemented that. And if I can find, I think it's in the specs. Yeah, portability, I think is the one. Yeah, here. So this is the thing that it is basically it's guaranteeing, like 8-bit bytes, addressable, two's complements, IEEE, little endian, memory regions can be like, this is the thing that, yeah. This is the thing that it's going to guarantee within all browsers or all execution environments. What's been happening recently with WebAssembly is that it's not always now being run within browsers. There are like command line tools that will run WASM files. So that's also been cropping up. Yeah, so these are the guarantees you have. Anything else someone has to do for you, or you have to map that over. So, yeah. Cool. All right. We are at the home stretch. Okay, so let's summarize the walls that we've encountered so far. So the files that you have need to be served while developing. So you have to have a web server or some way to get the files. Any functionality that you depend on, for example, operating systems, need to be implemented or given to you. Right? Data needs to be primitive or converted in some way. Bingo. Memory size and memory growth needs to be thought about because, yeah, the sandbox isn't infinite. And any required files that you have need to be embedded or preloaded. So, one more thing. Since we have 15 minutes, who's here old enough to do a Columbo reference? Half the crowd. Awesome. I love Columbo. One more thing. Let's use this one. This is the project. Well, numbers of a project. So we have the actual game, we have the hello world, we have the game logic, and then the full game. So these are the things you can look at. I have 3 extra ones. And here's the curse of live demos. I haven't run them in a while, so let's have fun. Yeah, let's open that one. Let's open this one. Who wants to play Wordle? Who likes Wordle? What's going to be the word? Demos. No, that's not the word. Okay. Come on, 5-letter word. Playing, huh? Care? Paris. An I somewhere. No, Indigo is too long. So yeah, I made Wordle. Let's cheat. It's try itchy. Ah, I'm so good at Wordle. So I made. So if you look at the repo and then play with this or try it out, you actually have 2 projects. You have the little game, the box moving game, and you also have Wordle. So in the same vein, there is the regular one. Here's all the answers if you want. It's quite a bit of a big file. Yeah, 25,000 lines. Don't worry about it. And then you have Wordle, and then you have the HTML. So this is just the JavaScript version. Then we have the, yeah, we can open this one. I think this is the one if anybody is photosensitive or like light sensitive, might want to look away for a second until I do this. This is a Wordle solver. So it will try. So I cannot try to make like a Wordle bot, like an AI, try to solve Wordle. It's not very good. You can improve it if you want. But what is happening is, if I refresh it, I can make it a little smaller. It's able to do about 30 games a second. It's winning about half of them. It's a very greedy approach. But here's the thing. What if we move it over? So let's move that over to WebAssembly. If I build it and run, I have the same. And you'll notice a thing that's happening. It's not faster. Why? Any thoughts on why it's not faster? Yeah? yeah, that was the thing I thought about. That going back and forth every time might be a blocker. I did a version that doesn't render. Sorry. So yeah, that's kind of the So being capped or rendering are the two suspects. Rendering was not one of them. As I mentioned before, anytime I go back and call the update function on the WebAssembly end, it's a time that I get to do work. Then I do whatever work I need to do, and then I yield back to the browser. So this will run at 60 FPS no matter what. So what I would have to do is I would have to run this in a thread or offload the work or like do as many Wordle games as I can within 16 milliseconds and then like yield my time. So I'd have to think about things a little bit differently. So just implementing it over wouldn't work. Yeah. Yeah. So questions about like webworkers and mutexes and threads. When I started to make this talk, so threads aren't in WebAssembly. I think they're not. I think they're voted in, but they're not standardized yet. I think they're going to come in with the next big version. But most of the browsers have implemented them. So Chrome and Firefox and the others, they have implemented threading. I will not go over how threading works because when I started this talk, it wasn't that big of a thing. You could probably offload some of the works to the web workers on the Emscripten end, or use regular threads on the C++ end. But the case is always that you need to yield the time over, or let the browser know when it can draw, or tell the browser to draw as much as you want. I'll let you know when I have new data, right? So you need to think about things in a little different way if you want to have some performance there. But that's one of the catches that will catch people off is if you try to do work as fast as you can, you're still limited by the browser frame rate. And not a lot of people think about that. Browsers have frame rates. They're usually 60 FPS. So you can play Wordle. So, any further questions? Before I switch over from Colombo? Yes, you had a... Calling WebAssembly from C++. I don't understand. You can call from both sides. You can call a thing from the C++ side to the JavaScript, and you can call from the JavaScript to the C++ side. You can do both ways. You would then be calling from native C++ to WebAssembly C++. I have not tried that. You should try that and let me know. But again, that WASM file that you had there, that's the only thing that's happening. That's the only world you have. So if you wanted to call C++, you would have to go out from that world. And the only way to go out from that world is to go into some sort of execution environment, which is usually a browser or the command line tools that people have been having. So that's the path you've been going. There's no other path out, technically.